of energy expenditure and fatigue by talking about the concepts of oxygen deficit and excess post-exercise consumption. Oxygen consumption, it's not in there, but it should say oxygen consumption or EPOC. All right, so here are the 4 topics for today. So we're going to start out by looking at this figure here. And so notice that, so the green is where we've resting energy expenditure. So y-axis, we've got VO2, x-axis, we've got time. So here we're just resting. And then at this point right here is where we start exercise. Okay. And we're going, our intensity, we're increasing such that our VO2 requirement or our oxygen requirement is this blue line. Now notice we don't immediately get to that place, right? We're not breathing enough, our cardiac output's not high enough. And so for a little while, we're in what's called an oxygen deficit, okay? And so remember, increasing workload requires a larger amount of oxygen. So what we mean when we say VO2 does not respond, that means we're not breathing in enough we're not bringing in enough oxygen to meet the demand. Okay, and so if we don't have oxygen, how are we creating energy? Because without energy, there's no work. And so when we're in these times of deficit, so any time that this black line is below the blue line, that's paid for by anaerobic systems. Remember that your anaerobic systems are constantly working, but depending on what's going on, it determines which of the energy systems you're relying on. Okay, and so this takes time. So we'll reach what's called steady state that we've mentioned a few times after a couple of minutes. And once we've reached steady state, what we're saying is our energy requirement is being able to be met by the amount of oxygen that we're using. Okay, and so initially relying on anaerobic systems, or at least a lot of it is being relied on by anaerobic systems. But once we reach steady state, then our oxygen is able to kind of pick up the slack. Now we continue exercise and then we end exercise, and that leads us to this excess post-exercise oxygen consumption, or EPOC. Okay, and so what this is when you stop exercising, your VO2 is still higher than normal, and it can take minutes or hours to get back to normal. During this time, your body's trying to get back to the resting energy level, but this doesn't happen. Okay, at least not right away. And there's a couple of components to it. So we've got a fast component where we're replenishing the phosphocreatine for the ATP phosphocreatine system. We're also replacing oxygen stores that are in your muscle and in your blood. Now, it's important to know that while we're replacing these stores, it doesn't take a lot of energy or effort. Like even at the end of maximal exercise, if we were to put like a saturation monitor on someone or even measure what the oxygen is that they're using, we are almost always completely saturated, okay? We'll talk about this later, but like the guys that use, like the big linemen that score a touchdown after running, 100 yards, fumble recovery, or whatever, and they're breathing oxygen, doesn't do a whole lot physiologically. Psychologically, there might be a difference, but physiologically, not a whole lot. Okay, so then why? Well, we've also got this slow component. So we've got increased heart rate still, body temperature's higher, we've got lots of epinephrine floating around, gluconeogenesis is going on from the lactate that's been produced. And so all of these require energy. All of these require oxygen. And so this is likely at least part of the explanation as to why oxygen consumption remains elevated after we stop exercising. Okay? Ultimately, it comes down to if we're doing more work, then we're going to need more oxygen. So even at the end of exercise, when we stop running, our body's still working, right? Because of all of these things that are going on. And so it takes a little while. We're going to transition a little bit to talk about something that endurance athletes are notorious for kind of paying attention to, and that's something called the lactate threshold. So what I want you to do before I start putting slides up is just look at this figure here. So we've got percent VO2 max on the x-axis, we've got lactate concentration on the y-axis. Untrained individuals in the red, and then once they become trained, they're in the blue. So what's the difference? All right, and so as you're thinking about that, I want to remind you of a couple things. Lactate does not cause fatigue, nor does it cause soreness. In fact, As many of you put on exam 1, lactate acts as a buffer. It picks up those hydrogen ions. Okay. Lactate is produced if we've got excess pyruvate, if we've got excess hydrogen ions, if there's not enough oxygen. There's all sorts of reasons why lactate is produced. Okay. Another thing is another reason why lactate is beneficial is we can use it as energy. We talked a couple weeks ago about how your heart really likes lactate for a fuel source. Okay. So lactate is great. So what is it with the lactate threshold? Well, remember, lactate is correlated with fatigue, but it doesn't mean that it causes fatigue. All right. And so when we get to these times where our lactate increases, it just suggests our body's not able to use it. And this is likely due to the lack of oxygen. There's not enough available oxygen. And so we start having to produce more lactate because we're relying on these anaerobic systems. And we're trying to buffer out that hydrogen ion. Okay. So when we train, and this is aerobic training, it results in two things. We have reduced production of lactate, and we increase the clearance. In other words, we're able to get rid of it out of the bloodstream, convert it to glucose, use it as a fuel source or whatever. All right. What we do know is that if we're better able to use lactate, we're better at aerobic activities. And so what happens is where this threshold, which is the place where we go from the flat curve to now we get the steep curve, we shift that to a higher intensity. Okay. What a lot of endurance athletes do, and I don't know if they still do it, but I know that a couple of previous coaches for the cross-country team here did what's called lactate threshold training. And basically when you're at your lactate threshold, you can hold that intensity for quite a while because your body's able to kind of clear everything out, maintain like homeostasis basically, or a steady state for a long period of time. And so you're working your muscles as hard as you possibly can, but you're doing it for a long period of time. Okay, and so this person will be able to go for a longer period of time at trained as opposed to untrained. All right, last thing is something called the economy of effort. All right, so we've got two runners. They're the exact same thing except for they have different economies. Now, what does that mean? Well, if you look at their speed, okay, for a given speed, their VO2 is different. Okay, and this is likely due to their economy of effort. And so what we mean by that is how much work are they using? Okay, so think about a car with miles per gallon. Well, we don't think about humans in that way. We think about it more in terms of VO2 per speed, so VO2 per miles per hour, something like that. With running economy, it's just how much oxygen are you using for a given pace, intensity, that sort of thing. As we've mentioned before, a given intensity requires a specific amount of oxygen. So if I have two people that are the exact same, they should require the same amount of oxygen to go run a 7-minute mile. However, it's possible that one of them will have a much lower VO2. Okay, and this is likely because they have a better running economy. All right, so what that basically means is that they're getting rid of anything that is unnecessary. Now, I should have a GIF of Phoebe from Friends running. And if you've ever seen that episode of Phoebe running, it's where Rachel doesn't want to associate with her. And then at the end, they're like, oh, this is cool. Let's run run however we feel comfortable running. The way Phoebe runs is very inefficient because her arms are waving around in the air and just kind of going nuts. And so she's running, but she's using all this extra energy waving her arms in the air. So she would have a low economy of effort. As the Olympics are on, watch the Olympics, and especially watch the speed skaters or the cross country skiers. They're very efficient with their movements as opposed to if you or I are doing that same thing. So I really wish that they would show an Olympic athlete and then they would show like an average Joe and just show them doing the same thing. One, you would see the difference in speed, and two, you would just be able to see, wow, the elite athlete, very smooth, no wasted energy, no wasted effort. And then you've got, Dr. Davis over here that's flailing to do whatever event that they chose me to do. So finally, what makes an aerobic athlete successful? Okay, they're going to have a high VO2 max, they're going to have a high lactate threshold, and they're going to have a high economy, meaning that they're very efficient with what they do. Ultimately, they'll also have a high percentage of type 1 fibers, which means they've got lots of muscle, they can use lots of oxygen, so they can go for a long time. All right, so Can you do the following 3 things at the end of this lecture?